So, good morning everyone. My name is Mark Angelo M. Moncada of BSCS 21D, and this topic is all about one-way infinite Turing machine. But first, let me show you a two-way infinite Turing machine. So, as you can see, this Turing machine is infinite at both directions, the left and the right part. But a one-way is only infinite at one direction, here, which is the right part, like this. But according to the theorem, every language accepted by a Turing machine M sub 2 is also accepted by a Turing machine M sub 1 with the following restrictions. So let us see first what this theorem is pertaining to. So this is the M sub 2. Here the M sub 2, the Turing machine M sub 2. And the Turing machine M sub 1 is the one-way infinite Turing machine. So the first restriction is M sub 1's head never moves left of its initial position. So here, as you can see, the cell here is the initial position or the partition point where it is divided. So you can see that it can't go left anymore because this is the limit already. So the next restriction is M sub 1 never writes a blank. So every time this head is being transferred to another cell, this input symbol can be replaced by a type symbol of just a blank. It must be another value. Also, according to the theorem, the two-way infinite Turing machine is equivalent to the one-way infinite tape Turing machine. So, in order to convert the two-way Turing machine to one-way, we are going to divide this two-way infinite tape depending on the partition point. So this right part of the partition point represents the upper track of the one-way infinite Turing machine. And the left side of the partition point, the cells that belong to the left side of the partition point, represents the lower track. So this is the lower track, wherein it must be in reverse order. As you can see, the head pointed in A, the input symbol A, is now located at the last part here in the lower track. So the diamonds here represents the blanks. There are many representations of blanks, but we choose to use the diamond as its representation. Here you can see Q sub 1. This is a state. This arrow here is the head. While this letter A is an input symbol. So here, when it transferred, the head transferred, there is already a new state. And when there is a new state, the input symbol was replaced by a tape symbol. If you can remember, this is letter A previously and was replaced by a tape symbol, letter G. So before we proceed, you must remember that because there are separated tracks, which are the upper track and the lower track, there must also be a separate number of states for them. If the two-way infinite Turing machine have a state of Q Q sub 1 and Q sub 2, the lower track and the upper track must also have their own, wherein there must also be included the direction or the track where it belongs. L for the lower track and U for the upper track. Here we are given a transition from the state Q sub 1 to state Q sub 2. Let's see it in the tape. Here in time 1, the Q sub 1 state heads to the cell of the input symbol A. In order for A to transfer to the another state, Q sub 2, it will be replaced by a tape symbol G. Here, it is replaced by a letter G tape symbol, and the head transferred to the right, and a new state was produced. So here, at the border, you can see it in the tape that the head was towards the special symbol. So what will happen in the transition is it is going to input a special symbol, and it is coming from a state of a special symbol also, that will be going to a special symbol that will also write a special symbol. The purpose of this is to transfer from this part of the special symbol to the upper special symbol, so that it can travel in the upper track.